Okay, perfect. So good afternoon, everyone. So I'm going to give you an overview of the results we have obtained over the last 8 years on the landslide hazard assessment in the North Tanganyika-Kivu region. And so, first of all, I want to stress that this is a work in collaboration with different partners. We have about 10 African partners, and here I listed the PhDs that I have worked with or that I'm currently supervising that have contributed a lot to what I'm going to show now. So to recap briefly about the study area, so the middle figure represents the landslide susceptibility assessment at the global scale. And so we see that this NTK rift is Africa hotspot in terms of landslide potential. It's much less than, for example, what we have in the European Alps. But interestingly, when you look at the population density, urban growth, and this kind of parameters, we really have a global hotspot in terms of exposure to landsliding. So this is the figure which is at the bottom of the slide. So more specifically in the region, so if I look at the northern part of the region, we have the city of Goma, and it was a highlight by Juliet about the Nyiragongo eruptions, so to see where we are. So I'm going to show regional results, but also specific focuses on the city of Bukavu, for example, and the city of Bujumbura, which is along Lake Tanganyika. So the region is having a tropical climate, so we have intense rainfall, so which is one key parameter for landslide to occur. We have also a deep weathering, but we have also lots of high population density, lots of environmental changes, urban growth, and interestingly, we are also in the rift. And so the figure to the B level, so to the right, shows profiles across the rift with the highlights of the rift shoulder and the differentiations between two landscapes. So basically, between the two rift shoulders, we have what we call the rejuvenated landscape. So this is where the erosion has been more recent through migration of nick points, for example. And outside this rift shoulder, we have a relatively older landscape, which we call relic landscape. And we show you that it has importances into the landslide distribution in the region. So the region is pretty large, and we have a high diversity of landslides. So some are very large and involve like entire mountains and are purely of geological origin. Others are much more recent. And for the recent landslides, we clearly see like clusters of landslides that are associated with heavy rainfall, convective rainfalls. But we have also clearly landslides that are associated, for example, with road construction or mining activities. So to work on this region, we do have, the key questions behind is like what type of landslides, where, when do they occur, what are the environmental factors behind, and also what is the human signature in these. And in terms of method, we are quite pluridisciplinary. So we have, of course, remote sensing, optical sonar imageries. We go in the field. We look at historical photos. We have also networks of citizen scientists. And we do have a strong partnership with African institutions. So we have currently more than PhD students working with us from this region. So one of the first results here at the regional level. So we have mapped more than 20,000 landslides from different sites, from different ages. And of course, we can derive from that typical susceptibility assessment that allow us to pick up the overall trends, for example, highlighting that the large landslides are having preferential distribution along the rift fault systems, for example. So looking at the trigger conditions, so we have looked at the dated landslides that we have, and that's an information that is very difficult to capture. We have about 250 dated landslides so far. Here, this is a map with 152 dated events over the last 20 years, and looking at also the earthquakes that have occurred in the region. Here, the earthquakes where a magnitude higher than 5.5 have been specifically highlighted with an impact zone, which is typically like seen as the zone that an earthquake can have an impact on the slope to trigger a landslide when it occurs. And we show that there is no link at all with the recent landslides and seismic activity in terms of triggering. So we clearly show that over the last 20 years, all the real landslides events that have occurred have been associated mostly with rainfall. And so in that figure here, the figure B, so you have the monthly average rain that shows the alternation between the two wet seasons and the driest season, which is in June, July, and August, and the landslide peak, which is represented here by the black curve, clearly shows that there is a landslide activity peak at the end of the second rainy season, showing also the importance of antecedent soil moisture condition in the processes. So these are examples here of landslides that are triggered by rainfall. And also what I want to stress in the multi-hazard framework is that those very, let's say, specific events are very often compounding with flash floods, as highlighted here and for the Lake Kivu region. So we have looked at those shallow landslides and the way also they are distributed with respect to the rejuvenation of the landscape. And so what we show is that overall you have a higher landslide rate that is occurring in the rejuvenated landscape, so within the rift, as compared to what we have outside the rift. But interestingly is that we show that the landslides, they are more frequent, but usually smaller. And this smaller size, we hypothesize that it's due to less regolith availability. I mean, the landscape is younger and so less weathered in principle. And we have also more seismicity, so not as a trigger, but as a preconditioning factor. So you have an increase into fracturing that allows a smaller piece of the slope material to fail. So we've looked also at the shallow landslides with respect to deforestation. And so in this diagram here, year 0 shows the moment where you have a deforestation. Then you see that you have a landslide rate that is here pictured on the y-axis, and you clearly see after a few years that you have an increase in the landslide rate. So you have kind of a pulse of landslide activity, which will last over about 10 to 15 years. And so quickly, I'm not going into the details. So we know that deforestation has an impact on shallow landslides. We have the susceptibility patterns. So we reconstructed from historical photographs 60 years of yearly deforestation. For every year of deforestation, we have a new year of susceptibility. Combining that over the long term, we have a hazard assessment, and then we can go to exposure, vulnerability, and risk assessment. And here, this diagram shows the main mechanisms about risk assessment and how we explain that over the last 70 years, the risk of landsliding has increased in the DRC as compared to Rwanda and Burundi, where it's roughly stable. And this is due to one deforestation component, but also due to the fact that people are just migrating towards the most hazardous hill slopes, for example, due to mining activities that are quite substantial in the region. So zooming into the city of Bujumbura, so this map here with about 1,000 landslides pictures the hill slope that are just east to the city. And in the middle of the map, you have this brown dark line, which shows the delineation between, from one side, the rejuvenated landscape and the relic landscape. And clearly, you see the role here of landscape rejuvenation on the occurrence of landsliding. So that's one first aspect. Then a specific case here about multi-hazard. This is what I've called like landslide events. So you have an event here in A with heavy rainfall, more than 200 landslides occurring at once, different types of landsliding, but it has also occurred in a region where we have lots of quarrying activities. And so this quarrying debris were also reactivated with the rainfall, blocked the river system, as you can see here in B, then the flooded river also with debris provided by the landslides, and have, let's say, breached the dam, which increases the flood impact, and arrived and in town about 10 kilometers downslope and killed more than 100 inhabitants in just a few tenths of minutes. And although in town it was not raining at that moment, so increasing the importance of local disasters here. So now I'm moving towards what we call slow-moving landslides. So there are large, deep-seated landslides, and on this specific landslide that we call the Ikoma landslide, which is developed in highly weathered material, we have different components of the landslides. I'm not going into details here, but what we were able to do is to show that this landslide in the 50s was very small. Here, this is the red delineation, and then grew through time, and recording all the phase of man development and having investigation also in the field and discussing with local inhabitants, we could see and reconstruct the history of the landslide and show that this activity of the landslide is not associated with any kind of specific trigger. So no specific like rainfall periods, more humid periods, nor with earthquakes activities, stressing the control here of weathering and hill slope evolution. Then we've managed to, for the last 5 years, to document the deformation of the landslide at a weekly basis using about like 600 remote sensing images. And we show that on this weekly basis, the control is mostly associated with a quick response for rainfall. And earthquakes, again, doesn't play a role in this, let's say, weekly dynamic of the landslide. That's the same result that we have obtained here for the landslide, which is in the city in Bukavu in Congo. So that landslide here, highlighted in yellow, is inhabited by about 80,000 inhabitants. It's a slow-moving landslide. And we also show that on a weekly basis, like it's mostly rainfall, but no earthquakes that are associated with the dynamic of the landslide. And basically, we also show that there is an increase of the activity of the landslide at some point, which is due to urbanization. So as a last overview, so far I have highlighted the role of rainfall, I have highlighted the role of weathering on the shallow landslides. I have highlighted also the role of rainfall on slow-moving deep-seated landslides, but now we have looked also at the occurrence of large landslides. So for that, over 20,000 square kilometers, we have historical photos that have been used. We have mapped about 1,000 new large deep-seated landslides that have occurred in the region. And again, the patterns of these landslides and the record with the seismicity doesn't show any link between seismicity and landslides here. But I want to stress that we are the rift and we are sure that earthquakes play a role. It's just like the return period of, let's say, earthquakes of high magnitude is too long with regard to the 60 years observation we have to really make a strong link between earthquakes and landsliding. But when we look at the largest old landslides, some of them are clearly in cluster along the main fault systems. So with that, I thank you for your attention.
Thank you very much for this very interesting presentation. I think we've got a couple of minutes for questions from the audience. So the chat is open there to receive your questions. In the meantime, let me just stress how important I see the convolution of data from different disciplines that you have to calculate, let's say, the evolution of landslide risk, because it obviously depends on rainfall data, but also on seismic data in order to interpret what is the contribution of different hazards on what you see as landslide, which is a hazard per se, but also the result of other hazards. So do you have any collaboration with other disciplines in merging or convoluting such type of data?
Yes, yeah. So we do have, so I highlighted that in my first slide. So for example, for the rainfall in itself, so we have installed our own rain gauge networks in Congo, Uganda. So we have about 50 rain gauges. We work with different African partners there. We have also weathers from Burundi, from Rwanda, for example. But although with 50 rain gauges, we don't go that far. So we have used satellite products from iMerge. So this is, and we have directly collaborated with NASA, for example. This rainfall products being released every 3 hours, 7-kilometer resolution, and they show very good agreement, I mean, in terms of validation. For seismic data, so I do work with colleagues here, for example, at the Africa Museum, like Damien Dalvaux, who's been working a lot in the Rift about mapping faults and working with the Africa Array. But we have also collaboration with our colleagues from Luxembourg, so they have set up with the GVO in Goma, but also with other partners in Burundi and Congo. They have set up a local seismic network, which also allow us to have lots of seismic information and accurate seismic information to validate this. So we clearly do work with different parts. For having accurate dates about the landslides, we have citizen networks that have been implemented in the Rizombi Mountain, in Kigezi Highlands in Uganda, but also in DRC with the civil protections there. So where they have, let's say, tools that allow to report any kind of hazards. It's not about landslide, flood, hailstorms, drought, pest and diseases even. And so with that, we collect also information. So, and when I said the PhD students, we have currently more than, in our group, we are about 20 people to work on the hazards in the region. Some people, it's more like on the volcanoes, others about seismic hazards, but altogether, this feeds the landslide story. Your micro is mute.
It is, thank you. So I think one of the most important objectives of this webinar, that is followed by another two, is to bring people together from different disciplines. So to act as a platform, if you like, for exchanging data and ideas. Also, Fred presented previously a set of activities for the entire region, and other speakers previously. So this is just an opportunity to get in touch within us and put the things on the map with common formats, common data protocols, to be able to, digest the information and produce something useful for the local communities. For the interest of time, I think we need to move to the last presentation. So I would like to thank you once more for your contribution.
Thank you.
And we'll come back during the wider discussion. So
Okay, thank you.